Hi there. Today we're going to solve this problem called find a minimum in rotated sorted array. In this problem we are given a sorted array and we have to find the minimum element in it. The array might be right rotated n number of times. What do you mean by right rotated? Suppose we have an array 1, 2, 3, 4, 5. If it is rotated one time, we will have 4, 1, 2, and 3 right rotated. So that means some elements from the end of it will come at the start of it. If it was rotated two times, then we will have 3, 4, 1, 2. Right. But the array is sorted. Okay, and we have to find the minimum element. So the easiest way to do that is that we uh, take a variable and iterate through the array and assign the minimum to that variable, and that would be our answer. That would give us a time complexity of over 10. But there's another way of solving it using linear search, that whenever we encounter an inflection point. What do I mean by inflection point? Whenever we encounter an element which is bigger than the last element that we encountered, then this is an inflection point and the current element is the minimum element of the sorted array. So that is another way of solving it, and let's code it. So I'll just remove this now. Let's get the size of the array first. Nums.size, and then we iterate through the array. We should start from I of 1 because we're going to check uh, I minus 1 element. If nums of I minus 1 is greater than nums of I, then we will return the current element, nums at I. Right. And if that all doesn't work, we will return nums of 0. This will work when size is equals to 1. Sorry, there should be 2 equals to. Right. Are we missing something else? Yes. We have to check if the array is already sorted. If already sorted. If the number at 0 index is already less than nums at last index, then our answer is at nums at 0. Right? Will this work? Let's check. Works for the basic test cases and is submitted. Right. So this gives us a time complexity of over 10. But it is given in the question that we must try to write an algorithm that runs in O of log n time. Well, O of log n time, that means binary search. Of course, it is a sorted array. Whenever there is a sorted array, we can in some way use binary search. Although it is rotated, it is still a sorted array. Now, how can we use binary search in this question? So whenever we use binary search, what we are trying to do is we are trying to eliminate one half of the array that will not have a result. Suppose we have checked that left half of the array will not have a result, then we eliminate it and move our left pointer to the middle. And if the right half does not have a value, if we have determined that the right sub-array will not have our value, then we will move our right pointer to the middle, and so on. Okay, so how can we eliminate halves in this question? We can by saying, if we, let's take an example. Suppose we have this array, right? Our left pointer would be here, and our middle pointer would be here, and our right pointer would be here initially. Let's remove the mid for now. Let's just say we have our right, lower, and yeah, just left and right pointers. So our middle pointer will then point at 5. Okay, and we will check. First, we will check if the array, if our current array, our left and right pointer, the subarray formed by our left and right pointer, is it already sorted? How will we check that? If the nums at L and the nums at R, if the number at L is less than number at R, then it is already sorted. And if it is not sorted, we will go on and check if the right half will have our array or the left half will have our answer. Sorry. So how will we do that? First, we have done this, and we are checking if the array is already sorted. It is not sorted. So what we will do is we will find the middle. Middle will be at 5, and now we will check if our middle is greater than our value at L pointer. Yes, it is greater than our L pointer. So that means that we are in the bigger half of the array. We are in the bigger half. Why? Because the middle value of our array is greater than our left value. So we are in the bigger half, and our lowest value will not be in the bigger half. So we move our left pointer to middle plus 1. Our left pointer will go, our left pointer will go here. Yes, our left pointer will go at 1. So now we will check if our array is sorted in the next iteration, and we see that it is sorted, and we can return the answer as the element at L pointer. I'll go through it again. In binary search, in each iteration, we try to eliminate one half of the array that will not contain our answer. Okay, and the way to eliminate is that we can use conditional statements. And for the current question, we are checking uh, if we are in the bigger half of the array, our value would not be in the bigger half, and we'll have to move our left pointer to the mid. And if our right value, if our middle value is greater than, is less than or equal to our left value, then we are in the shorter half, in the smaller half of the array, and we have to move the right pointer to the middle. Okay, let's code this approach. Let's get the size first. Now let's just get the R pointer, which will be nums dot size -1, and left pointer would be 0, and let's just begin our while loop. While L is less than R, we will continue the binary search. If it is already sorted, if already sorted, if nums of L, if the number at L pointer is less than the number at R pointer, then it is already sorted, and we can safely return the number at L pointer. Otherwise, if that doesn't work out, we'll find the middle, which will be L plus R minus L divided by 2. And if you don't know why we are using this instead of saying L plus R divided by 2, We are doing this because we want to avoid integer overflow. Why? Because L plus R both might be 10 to the power 9, and when we add them, they will go bigger than the range of integer. So instead, we subtract them, divide them by 2, and add L later. Okay, and yes. So if now we check if we are in the bigger half, how will we do that? If the number at our L pointer is less than our number at our middle pointer, then we are in the bigger half, and the value will be in the smaller half. So we have to reassign our L pointer to middle plus 1. Else, if nums at L is greater than our nums at M, or if there's any other case, then our R becomes M. And after the value, we will return the number at L pointer. That will be the lowest. And this is for the smaller half. This is to eliminate the bigger half. Eliminate. I hope the spelling is right. Eliminate. Okay. Let's see if this works. It works for the basic test cases. And it gives wrong answer. Why does it give wrong answer? That should not have happened. It is right rotated by only one element. That means 2, 1. We have 2, 1, and my code doesn't work for this test case. Why might it happen? So this case doesn't definitely run for it if because it is not sorted. L has to be less than R, and nums at L is not less than nums at M. So we move our left pointer to n plus 1. So let's go through it. Let's just go through it. If we have 1 and 2, our left would be here and the right would be here, and our first middle would be at L pointer only because the middle is size divided by 2. Sorry, L plus R divided by 2. Our middle would be here, and we are checking. Oh, sorry, the array is 2, 1. We are checking if nums at L is less than M. No, it is not. So we will move the right pointer correctly. Okay. No, we should not move the right pointer here. We should not move the right pointer. If it was less than equal to, we don't want to move the right pointer when the left and middle pointer are at the same place. It has to be less than equal to. Will this approach work? Yes, it works. So again, the time complexity of this algorithm would be O of log n. Thank you.